I want to talk about chords, angles, and circles. Um, uh, and We've already discussed to some degree that if we have a circle, let's look at this circle here, the white circle drawn. Uh, we know that the radius of the circle is the line that goes from the center of the circle out to the edge of the circle. And you remember that the definition of a circle is the set of points, all of which are an equal distant from that center point, and the length of that distance is called the radius. We know that the tangent of a circle is a line that's exterior to the circle that just touches it at one point right here. And indeed, we've also talked about how with the tangent is such that if we draw the line from the center to the tangent, like that, um, draw the radius that goes from the center to the tangent, that angle here must be 90 degrees. Okay, we've shown that, or at least we've talked about that. Now, it's also true that if we look at the line which goes from one point on the circle across the inside of the circle to another point on the circle, we call that line the chord of the circle. So, three critical lines that we draw inside a circle. The red is the radius, the green is the tangent, and the blue one is the chord. Now, some simple properties about chords. If we have two chords, as shown over in this circle right here, if we have two chords of equal length, so this chord, say, equals this chord, you might say that the chords are congruent. If we have two chords of equal length, then we talk about the length of the arc that they subtend in the same circle is equal, and that this angle interior right in here, these angles are equal. Okay, so two chords are the same length. This arc length equals this arc length, and this angle equals this angle. It's relatively simple to prove. If the chords are equal length, then we have that this line and this line are congruent. All the red lines are radiuses, so all the red lines are equal. So we have a side, 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 and side here. So we have side, side, side equals side, side, side. Obviously, then those two triangles are congruent. If the triangles are congruent, then these two respective angles right in here are the same. Okay, and then that means that the arc length subtended by the angle is the same. And if you think about the definition of angle in radians, that's pretty obvious. Okay, the next item for this lesson is to define what we mean by a central angle and an inscribed angle. Already we've been talking about inscribed angles, and about central angles. This angle right here is a central angle. This angle right here is a central angle. Why? Because one vertex is the center of the circle. Similarly, we take this angle here to be a central angle because one vertex is the center of the circle. So a central angle is one where a vertex is located at the center of the circle. An inscribed angle is exactly what it sounds like. It would be an angle where the points on the triangle, this would be an inscribed triangle here. So the points on this triangle are actually lie on the circumference of the circle. So this point lies on the circumference of the circle, and then we draw the line out to the circumference. This point is the same point on the circumference, and we draw this line out to another spot on the circumference. So we call this a central angle. We call this an inscribed angle. Okay, we're going to be talking a little bit more about properties of angles inside of triangle angles inside of circles, there's some interesting stuff here. Okay, so next time.